In this section, we're going to take a look at verifying trigonometric identities. Throughout this chapter, we're going to be looking at other identities, which are a little more advanced and a little more involved. So here, we're going to summarize the identities that we've seen so far. Then we're going to look at the examples of using these fundamental identities so that we can be prepared a little more to use identities in later sections. None of these identities that we see here are new. They are all ones that we've encountered in the first half of the course, and we want to summarize and see some examples in this short section before we go on to new ones throughout the second half of the course. So the fundamental identities that we have seen so far are the reciprocal identities, so called because they relate one function to another by noting that one is the reciprocal of another. So the cotangent of the angle theta is equal to 1 over the tangent of the angle theta. And vice versa is also true. We can also say the tangent of theta is equal to 1 over the cotangent of theta. Either of those is fine. One is the reciprocal of the other. We can say the same thing for the secant of theta, and that's going to be the reciprocal of the cosine function. Or we can also say that the cosine function is equal to the reciprocal of the secant function. Either of these is acceptable. They mean the same thing. And of course, the remaining pair also go together. The cosecant of the angle theta is equal to 1 over the sine of the angle theta. Or you can also say the sine of the angle theta is equal to 1 over the cosecant of the angle theta. Like that. And we see these identities when we first learn about the definitions of the sine, cosine, tangent, secant, cosecant, or cotangent off the unit circle. We also have the quotient identities, which we see the tangent of theta set equal to the quotient of sine over cosine, sine of theta over cosine of theta, and the cotangent of theta, being the reciprocal of the tangent function, is simply the cosine of theta over the sine of theta, or in other words, the reciprocal of this one. Also from the unit circle, in tandem with the Pythagorean theorem, we see the Pythagorean identities. Which relate sine with cosine, where the cosine squared of an angle theta plus the sine squared of that same angle theta, and that is important, they should be the same angle. If they're different angles, this doesn't work. Cosine squared of the angle theta plus sine squared of the angle theta is equal to 1. And we can reorganize these a few different ways to give us different versions of the Pythagorean identity, which relate sine with cosine. Another version will relate tangent with secant, namely tangent squared of theta plus 1 is equal to the secant squared of theta. And the third variety will relate cotangent with cosecant. So here we get 1 plus cotangent squared of theta is equal to cosecant squared of theta. And again, if these look familiar, they should. We are simply right now summarizing the identities that we've seen so far in the course. And when we looked at the graphs of sine, cosine, tangent, secant, cosecant, and cotangent in chapter 4, we reinforced the identity of these functions being either even or odd. So we have the even-odd identities, which state that the sine of the angle theta, that should be negative theta. The sine of negative theta is equal to the negative of the sine of theta. The tangent of negative theta is equal to negative the tangent of theta. The cosecant of negative theta is equal to negative the cosecant of theta. And the, let's see, which ones do we have? We're missing the cotangent. The cotangent of negative theta is equal to negative the cotangent of theta. And these identities, where the negative on the inside is equivalent to having the negative on the outside, this comes from the fact that these four functions are odd functions. Note, this means these four functions are odd. And then the other two remaining ones are even, which means that the cosine of negative theta is identical to the cosine of positive theta. Doesn't matter what the sign of your argument is, as long as the number is the same, the result's the same. And the same is true for the secant of theta, the reciprocal of the cosine. Just like that. And again, note this means that these two functions are odd. Oh, sorry, these two functions are even. These four are odd. All right, and this summarizes all the identities we've seen so far. We're going to go ahead and look at a few examples of using these. Again, these examples aren't exactly new. This section is largely a review of the first half of the course before we go on and look at other more advanced identities in the second half of the course. So some of these examples are going to sound reasonably familiar because we've seen examples similar to them in previous sections. So the first example tells us that we're given some information. We know that the tangent of theta is equal to negative root 7 over 2. And we know that the secant of theta is greater than 0. We don't know exactly what it is, we just know it's greater than 0, or in other words, it's positive. Okay, so now the question is, we're going to find the sine of the angle theta. And we want it as an exact value. Find the exact value of the sine of the angle theta. Remember, when we say an exact value, that means we don't want a decimal. No matter how many decimal places you have, it's always going to be rounded. If you grab a calculator, no matter how many decimal places your calculator allows, there's always some that it cut off, right? So no matter how big of a decimal you get, it's never exact. It's always just more or less. When we say we want an exact value, a decimal won't be sufficient. You want it in terms of radicals, in terms of roots, in terms of fractions, and so forth. Something like this, where there is no rounding at all. All right, so here, we remember that the tangent of theta is the sine of theta over the cosine of theta. Right? That is one of our identities, namely the quotient identity. But that runs into the problem that, well, notice the sine of theta equals to negative root 7. That can't possibly happen. Because after all, the square root of 7 is about 2.6, which can't happen for the sine of the angle theta. Remember, the sine of the angle theta must be between 1 and minus 1. Negative root 7 is like saying negative 2.6, more or less, which can't happen. So here, using the quotient identity is tempting, but it's not going to give you a valid result. So here, I wish I could use this one, but it's not going to work. Okay, so let me hunt around to see if I can find any other identity that helps me relate tangent to other functions. Here I could relate tangent to cotangent. Yeah, but that doesn't really get me any closer to finding the sine function. Okay. Over here I can relate tangent to secant. Oh, that's good, because once I know secant, I can use that to find cosine. And once I know cosine, I have other ways of finding sine. So let's do that. Let's go ahead and use the Pythagorean identity. Note that whenever you're using identities to find missing information, there isn't anything that necessarily tells you here's the right thing to do. Sometimes you're going to try something and it's just not quite going to work out. There's nothing wrong with that. That's part of the process of learning how to do this. So here, my first thought is I try this, but then when I try it, it gives me a nonsense answer. So that can't possibly be the right one to use. So here, I suspect this is the good one to use, but again, I might be wrong. I might have to go look for another one. So let's actually try it. Unfortunately, sometimes the only way to know whether or not you're right or not is to go through and actually do the problem. So, using the Pythagorean identity, we know that the tangent squared of the angle theta plus 1 is equal to the secant squared of the angle theta. Okay? But we know the tangent of the angle theta, that's negative root 7 over 2. So here I can write this as negative root 7 over 2. Now the whole thing's being squared, plus 1 is equal to secant squared of theta. Well, now I can actually do that. When I square root 7, I get root 49. Root 49 is just the number 7. Squaring a negative makes it a positive. A negative times a negative is a positive. Squaring 2 is 4. Plus 1 is equal to secant squared of theta. And then I can just add these. 7 fourths plus 1 fourth. 7 fourths plus 1 is like saying 7 fourths plus 4 fourths, which will give me 11 fourths. And so now I can find secant of theta by taking the square root of both sides. Whenever I take the square root of a number, there's two ways to do that. There's positive and negative. So here I have two possible answers. I get that the secant of the angle theta is either equal to positive or negative square root of 11 over 4. Now here, note that one of my pieces of information that was given is that the secant of theta should be positive. Oh, so since secant of theta must be positive, must be greater than 0, well then it can't be the negative 1. So that suggests that the secant of theta must be the positive square root. Here, when I take the square root, I can't take the square root of 11 as a nice number. I just have to leave it as root 11. But I can take the square root of 4. That's just the number 2. All right, so I find secant of theta is equal to root 11 over 2. All right, well, if that's the secant of theta, then that suggests that the cosine of the angle theta, now remember that is one of our identities, that's the reciprocal identity. The cosecant of the secant of the angle theta is equal to 1 over the cosine of the angle theta. This one right here. Secant of theta is equal to 1 over cosine of theta, which can equivalently be written with cosine of theta equals to 1 over secant of theta. Which is 1 over that number we found over here, root 11 over 2. And so now we can reciprocate this. 1 over a fraction. Dividing by a fraction is the same as multiplying by a reciprocal. So this is like saying 1 times the reciprocal of this, which is 2 over root 11. So we get that the cosine of theta is equal to 2 over root 11. Now, that's an irrational denominator, so we can always rationalize that. Here, we can rationalize by taking the square root of 11 and multiplying it on top and bottom. 2 times root 11. Root 11 times root 11 is root 121, which is just the number 11, like that. So now I have the cosine of the angle theta. Well, now the question was to find the sine of the angle theta. Well, there's a couple of ways I might be able to do that now. Notice I have tangent of theta, and I have cosine of theta, and I want to find sine of theta. Well, I have a few different ways that I might try that. For example, I have the cosine of theta. I can use this Pythagorean identity to find the sine of theta, and that'll work. Another thing I can do is, well, I have the sine, I want the sine of theta, and I have the cosine of theta and the tangent of theta. Well, this identity relates all of those. I have the sine of theta that I want to find, and these are two numbers that I know. I could plug them in and solve for sine of theta. Either of these will work. It doesn't really matter which one you choose. Here, since I've already used one of the Pythagorean identities, let me go ahead and do this one. That way I can have an example of different types of identities. But we could use this one as well. Either one would work. So I'm going to go ahead and use this one. Tangent of theta is equal to sine of theta over cosine of theta. We know that the tangent of theta is equal to the sine of theta over the cosine of theta. Now notice I'm trying to find sine of theta, so let me isolate that. Let me multiply both sides by the cosine of theta. Here these divide away. As long as they're not both 0, then this divides away. You say, what do you mean if they're not both 0? Well, if cosine of theta is equal to 0, 0 divided by 0 doesn't go away. That's undefined. We'll run into issues like that in later sections. So I wanted to call attention to that right now. Cosine of theta might equal to 0. And dividing by 0 is kind of an issue in its own right. So just be mindful of that. That's something we'll run into in later sections. But for now, we know that's not 0, because in fact we know what it is. So that's okay. If we didn't know what this was, and we thought, well, maybe it could be 0, that might actually be an issue. That might be something we couldn't do. But as I said, we'll see that in a later section. For now, this is fine. And we've isolated the sine of theta. So the sine of theta is equal to the cosine of theta times the tangent of theta. And we know both of those numbers. The cosine of theta is 2 root 11 over 11. And the tangent of theta is going to be negative, so times negative root 7 over 2, just like that. And now, note that 2 divides 2, so those go away. And here we can write this as root 11 times root 7. That's root 77. Now, that's a positive times a negative, which makes the whole thing a negative. And the only denominator we have to worry about is 11. After all, both of those are gone now. And that is our result. Tangent of theta is this. Tangent of theta is this. So the sine of theta turns out to be this one here. Just like that. Okay, for our next example, let's consider something a little bit different, something that we haven't exactly seen in a previous section. All right, so here we're going to be given an expression, and the directions read, we want to write the expression in terms of cosine of theta and sine of theta. Now, when they say and, it doesn't actually have to be both. If everything's written in terms of cosine of theta, that's fine. If everything's written in terms of sine of theta, that's fine. Or if it's both, that's fine too. So this is sort of an and or. Yeah? Cosine of theta and or sine of theta. Then simplify. So that there are no quotients. Okay, so let's take an expression. Let's say cotangent of theta times the secant of theta times the sine of theta. Okay, so here's an expression that's made up of the product of 3 different trig functions. We can rewrite those trig functions using only sine and cosine. Note that every function can be written in terms of sine or cosine. Here, sine and cosine are already the way they need to be. Secant can be written as the reciprocal of cosine, and cosecant can be written as the reciprocal of sine. Meanwhile, tangent and cotangent can be written as a quotient of sine or cosine, one way or the other. So here, since we're trying to write everything in terms of sine of theta and cosine of theta, notice that this is already the way it needs to be. It's already in terms of sine of theta. These can be rewritten. So here we can rewrite this to equal, well, cotangent of theta can be written as cosine of theta over sine of theta. Secant of theta can be written as 1 over the cosine of theta. And sine of theta is already just sine of theta. Okay. So here, the first part of the question is to write the expression in terms of sine and cosine, which we've done. Everything here uses sine or cosine only. The second part says to now simplify so that no quotients appear. In other words, can we reduce expressions? Is there anything that divides out, combines? Are there any like terms or anything like that? Here, you know, cosine of theta divides cosine of theta. That's just the number 1. Likewise, the sine of theta divides the sine of theta. And again, that's just the number 1. So here we're left with 1 times 1 times 1 divided by 1. Oh, that's just the number 1. And there we go. Oftentimes, we can write trigonometric expressions in terms of other trigonometric expressions. In fact, that'll be one of the biggest benefits to trigonometric expressions. When you deal with algebraic expressions, x, x squared, sums, differences, products, and quotients of polynomials, there aren't too many ways that you can rewrite things. Sure, you can change the order of things, you may be able to factor in some nice cases, but generally speaking, when you have a polynomial, you're pretty much stuck with that polynomial. Trigonometric expressions aren't like that. Because of the different ways you can rewrite one expression in terms of the other, you can rewrite an expression hundreds, if not thousands of different ways. That's going to be one of the biggest advantages to trigonometry. Essentially, you can never be stuck. If the expression that you have is not something that you can easily work with, there's other ways of rewriting it. And if those don't work, well, there are still other ways of rewriting it. The primary advantage of trigonometric expressions, of using trigonometric expressions, is that if the way they're currently written is not convenient, you can always rewrite them in any other way that is valid. Right? That's also, unfortunately, sometimes the disadvantage of trigonometric expressions. Sometimes you have too many choices. It's hard to tell which one's correct. But as we go through this chapter, we'll try to answer how to do that, at least to some degree. Let's take a look at another example. Same directions. We're going to write the expression in terms of cosine and sine of theta, then simplify so that no quotients appear. So here, let's just call this one part A. We'll call the next one part B. And for this one, we want 1 minus the sine squared of theta over 1 plus the cotangent squared of theta. Just like that. Okay, so first of all, we want to write everything in terms of sine and cosine. Incidentally, even if this is not in terms of sine and cosine, that's a constant, and we're okay with that. If ever you leave something as a constant, that's acceptable. But when we say write things in terms of sine and cosine, we mean the trigonometric expressions. Okay, so this is already in terms of sine. That's just a constant, and so is that. But this one can be rewritten. So let's go ahead and try that. And in fact, this is an example of one of the type of expressions where you have a few different choices. Note, the first thing we could do is we could just say, well, cotangent of theta, using the quotient identity, is just cosine of theta over sine of theta. And that'll work. We can write this as 1 minus sine squared of theta over 1 plus cosine squared of theta over sine squared of theta. And that's a perfectly valid expression. But then we actually have to simplify that part of the expression by combining like terms and then simplifying. Because remember, we also want to make sure no quotients appear. So here I'm going to do this one way, and that's by the way I just said. I'm going to write this in terms of cosine of theta over sine of theta. But then I'll do it a different way to show why sometimes the obvious choice may not always be the best one. So here we can write this as 1 minus sine squared of theta over 1 plus, and cotangent of theta is cosine of theta over sine of theta. So cotangent squared of theta is cosine squared of theta over sine squared of theta. Okay, so now everything's in terms of sine and cosine, and maybe some constants. The problem is now there's a lot of quotients. Here's a quotient there and a quotient there. All right? This is in fact a complex fraction, a fraction within a fraction. So we need to simplify. Now, going back to algebra, the way we simplify a complex fraction is we can go and combine all of these into a single fraction and then divide by the reciprocal. So right here I'm focusing on just this part, and I want to go ahead and combine these, and in order to combine these I have to add them. right, because of this. And in order to add, I need them to have a common denominator. So here, I'm going to write 1 as sine squared of theta over sine squared of theta. That way they have the same denominator. So 1 minus sine squared of theta, that's going to stay the same. Down here, and let me go ahead and put these in brackets just so that we can call attention to it. This is sine squared of theta over sine squared of theta. All right, sine squared of theta over sine squared of theta, plus cosine squared of theta. All right, if you divide these, you get the number 1. If you divide these, you get cosine squared of theta over sine squared of theta. Now, notice that I can now reciprocate. After all, I'm dividing by a fraction. And when you divide by a fraction, that's the same as multiplying by the reciprocal of that fraction. So I can leave 1 minus sine squared of theta the way it is. But now, instead of dividing by this, I can multiply by, I'll have sine squared of theta on top now, and sine squared of theta plus cosine squared of theta on the bottom. Like that. Okay? So now we've gone from having two quotients, one within the other. Now we have just one quotient. Here's one fraction multiplied by this expression. Notice, though, that right here I have the sum of the squares of sine and cosine. Anytime you have sums or differences of squares of trig functions, it should call to mind the Pythagorean identities. Notice the sine squared of theta plus the cosine squared of theta, and again that's addition, so you can do it in whatever order you like, is equal to 1. So right here, this denominator, sine squared of theta plus cosine squared of theta, is just the number 1. So here, that's just the number 1. And so now that's not even a fraction anymore. Sine squared of theta over 1, well, that's just sine squared of theta. So this is going to equal to 1 minus sine squared of theta times sine squared of theta. Just like that. We can simplify this further. Notice right here, cosine squared of theta plus sine squared of theta is equal to 1. And you say, yeah, but we already did that. And besides, I don't have any more cosine squares of theta added to sine squares of theta. Right here I have sine squared of theta, and I have sine squared of theta over here, but I don't have any cosine squared of theta anywhere. Well, yeah, but notice you have a 1 and a sine squared of theta. And those are 2 out of the 3 terms in the Pythagorean identity. Notice that if I were to subtract sine squared of theta from both sides, this would go away, and this would read cosine squared of theta equals 1 minus sine squared of theta. Let me do that off to the side over here. Note that the Pythagorean identity reads cosine squared of theta minus sine squared of theta, that should be plus sine squared of theta, equals to 1. And now if I subtract sine squared of theta from both sides, these subtract away, and we're left with the expression cosine squared of theta is equal to 1 minus sine squared of theta. This is another identity that comes directly by manipulating the Pythagorean identity. But now notice, 1 minus sine squared of theta, that's cosine squared of theta. So here we can write this as cosine squared of theta times sine squared of theta. And now we're done, because now we've written everything in terms of sine and cosine, and we've simplified everything away so that there's no more quotients, and everything's as simplified as we can get it. So here, cotangent of theta times secant of theta times sine of theta, that's equal to 1. On the other hand, 1 minus sine squared of theta over 1 plus cotangent squared of theta is equal to cosine squared of theta times sine squared of theta. And you know these look very different, they are exactly the same. What that means is if you were to pick any angle you want and plug it in, let's pick a random number, let's say 17. If you plug in 17 here and here, or if you plug in 17 here and here, you're going to get the exact same answer. Over here, if you plug in 38, and if you plug in 38 here, these will be exactly the same answer. That's what an identity means. Even though they're written in terms of different functions, they look very different, no matter what, these two, as long as you substitute in the same value to both, will always be equal. All right, so let's take a look at this one more time. Because of the different identities that we have, the fundamental identities, plus a few others that we'll see in later on through the chapter, there are other ways of rewriting this. Note right here, I ended up doing this at the end. I could have done it at the beginning though. Notice 1 minus sine squared of theta is cosine squared of theta. I can write that from the very beginning. Cosine squared of theta. 1 plus cotangent squared of theta. Well, I have an identity right here. 1 plus cotangent squared of theta. That's equal to the cosecant squared of theta. Just like that. Well, yeah, but then I can write this way. I can write this as the cosine squared of theta times 1 over the cosecant squared of theta. That means the same thing. 1 times cosine squared of theta gives me my previous numerator, and then this being the only denominator is the same as this. But now, given the reciprocal identity, 1 over cosecant squared of theta, 1 over cosecant of theta is sine of theta, so 1 over cosecant squared of theta must be sine squared of theta. So here this will give me cosine squared of theta times this now becomes sine squared of theta. And you'll notice that even though our steps look completely different, we end up with the same result. This is one reason why the identities should not be thought of as a single formulaic way of doing things. Rather, these are your options. These are not formulas to be memorized and to be thought of as, okay, here's what I need to plug in and here's how I'm going to get my answer. Rather, these are your options. Whenever you see the tangent of theta, that's one option, to rewrite it as 1 over cotangent of theta. Another option is to write it in terms of sine of theta over cosine of theta. And another option is to write it in terms of secant of theta using a Pythagorean identity. And in later sections, we'll have other options as well. Do not think of these as, here are formulas that I memorize, and whenever I see this, I plug it in here. Rather, these are the different options that you have, and depending on your problem, sometimes one option may be better than the other. In fact, notice here. This was significantly shorter than this. Although, even though this one was shorter, probably a little bit easier, you still get the same result. So even if you don't choose the absolute best route, as long as you use your identities correctly, you still will get a similar, or you'll still get the same answer. So for the last example of the section, go ahead and give this a try. Same directions, write the expression in terms of cosine of theta and sine of theta. That's your first part. And then simplify so no quotients appear. Note that in the end, your final answer doesn't have to be in terms of sine and cosine. For example, in this one, we ended up with a constant. It wasn't in terms of sine and cosine. But in this case, it was. So nothing says it has to end up this way, but that should be your first step. And then simplify so no quotients appear. So go ahead and simplify the following. We're going to take, and we'll just call this one part C, sine squared of theta plus tangent squared of theta plus the cosine squared of negative theta. So go ahead and do that. Simplify everything down. Remember, you should have everything written in terms of cosine of theta and sine of theta first, and then from there simplify so that in the end no quotients appear. Go ahead and pause the video, give that a try, and once you have a result, go ahead and unpause and we'll finish it off together. All right, so note that this argument is different from all the rest. All these are in terms of theta, but this one's in terms of negative theta. And again, we want to start off by writing everything in terms of either sine of theta or cosine of theta, not negative theta. Fortunately, we have an identity, the even identity for cosine, which says that the cosine of negative theta is the same as the cosine of positive theta. So here we can basically just say, okay, we don't want that negative there, so we just get rid of it. Note that doesn't work for every function. It works for cosine and for secant. Sine, tangent, cosecant, and cotangent functions are odd, so you can't just get rid of the negative. You can move it, but you can't just get rid of it. But for cosine of negative theta is the same as cosine of positive theta. So here we can just write this as cosine of positive theta. Okay, so sine squared of theta plus tangent squared of theta plus cosine squared of theta, like this. Okay. Tangent squared of theta we can rewrite as sine squared of theta plus tangent squared of theta, we can write that as sine squared of theta over cosine squared of theta plus cosine squared of theta. Just like that. Okay, so that's the first part. The first part was to write everything in terms of sine of theta and or cosine of theta, which we've done. But now the next part is to simplify things and write things without any more quotients. Okay, well, first of all, notice that this is the Pythagorean identity. Sine squared of theta plus cosine squared of theta. And you say, well, what about this part? Well, that part's separate. But these two together equal the number 1. Right? It might help if you write them together. It might help you see it if you write them as sine squared of theta plus cosine squared of theta. This is all addition, so I can just reorder things however I like, plus sine squared of theta over cosine squared of theta. And now here, that's the Pythagorean identity. Sine squared of theta plus cosine squared of theta equals 1. So that's just the number 1. Plus sine squared of theta over cosine squared of theta. Notice that I can write this together. I can put these together and say that's cosine squared of theta as both the numerator and the denominator. So I can write this as cosine squared of theta over cosine squared of theta plus sine squared of theta over cosine squared of theta. After all, that is still the number 1, but the reason I write them this way is because now they have a common denominator. And because they have a common denominator, I can just add the numerators. So this will give me cosine squared of theta plus sine squared of theta in my numerator over cosine squared of theta in my denominator. Oh, but that's the Pythagorean identity again, because after all, cosine squared of theta plus sine squared of theta in either order equals to 1. And that's what that numerator is. So I can now write this as 1 in my numerator over cosine squared of theta in my denominator. And now, remember, we want to write things so that there's no quotient. So here, 1 over cosine of theta, by a reciprocal identity, 1 over cosine of theta is secant of theta. So 1 over cosine squared of theta is secant squared of theta. And that's our result. Just like that. You may have gone a slightly different way about it. After all, there are a few options you can take. For example, at this point, you can say 1 plus sine squared of theta over cosine squared of theta. Oh, well, that's the same as 1 plus tangent squared of theta. Sine over cosine is tangent. So sine squared over cosine squared is tangent squared of theta. But now 1 plus tangent squared of theta, you can use that Pythagorean identity instead. And you would still end up with secant squared of theta. So as I mentioned a moment ago, in the previous problem, there are a few choices that you can make along the way. But in the end, we still get the same result. Because of the different ways that you can write trigonometric functions in terms of each other, there are tens of thousands, if not hundreds of thousands of different identities. Of course, memorizing all of those would be impractical, and in fact probably impossible. And having them all written down would also be rather impractical. Having a list of 10,000 identities to use, even if they're written down, it's going to be difficult to use. So what we do is we often remember a few basic identities, the Pythagorean identities, the reciprocal identities. In coming sections, we're going to see the sum and difference identities. We're going to see the half angle identities, the double angle identities, just a few basic ones that we use all the time. But what about all the others? Well, for all the others, we don't memorize all of these complicated identities, all of these identities that we don't use very often, and instead we learn to verify them as we need. Meaning, well, here is something that I think should equal to something else. Now, if it's something that I've memorized, great. But if not, well, we don't have to memorize it or even try to see if we can look it up somewhere, assuming we even had some kind of list with all of those identities on them. Rather, we can say, well, maybe we can just confirm whether or not that's true without anything other than what we already know, the basic identities. So in this section, you're going to note that we don't really have any formulas, any development, or any theory of that nature. This is going to be more of a methods section, where we're going to see the different methods that we're going to use to verify identities. All right. So for the most part, this section is going to be just examples. And through those examples, we'll see the different techniques. So for our first example, let's consider the following equation. The tangent squared of theta plus 1 divided by the secant of theta is equal to the secant of theta. Okay? Now, whenever you have an equation, that equation may have one solution, or two solutions, or 20 solutions, or it may not have any solutions at all. For example, thinking about just an algebraic equation, you might have something like x squared is equal to 25. And this equation has two solutions, positive 5 and negative 5, right? X is equal to plus or minus the square root of 25. So whenever you have an equation, usually you'll have one solution, or in this case, two solutions. And in fact, sometimes you won't have any solutions. For example, we might say something like x squared is equal to negative 1, which doesn't have any real solutions. Now, it does have an imaginary solution here, in fact, two of them, but it has no real solutions. However, you will sometimes find some equations that not only do they have some solutions, they actually have an infinite number of solutions. In fact, every number is a solution. So, for example, the equation x equals to x, the identity function, right? X equals to x. This is true for any number. 1 equals 1, 5 equals 5, 1/3 equals 1/3, and so forth and so on. This is called an identity. An identity is an equation which is true for any number, for any real number at least. We're not going to deal with complex numbers. For any real number. Now, sometimes identities are obvious. X equals x. Well, of course it is. But other identities are not obvious. So for example, this. Is this always exactly the same as that? If it is, it's an identity. Well, what if it's not always exactly the same? What if it only has some solutions? Well, then that's not an identity. Or maybe it has no solutions. So here is an equation. We don't know if it has one solution, like two solutions, three solutions, something like this, or if it has every number as a solution, or maybe no solutions. So here the question is to verify the identity. Whenever you see the phrase verify the identity, what that means is go through and confirm that in fact it is an identity. Confirm that this is equal to this no matter what the value of theta is. Now, of course, you can't do that by just substituting in numbers. Because if I came over here and plugged in 0 in both sides and said, oh yeah, both sides are equal, well, that's not good enough. If I came over here and plugged in 0 and plugged in 1 and 2 and 3 and 4 and 5, that still wouldn't be good enough. Because all I've done is I've confirmed that those are solutions. An identity should confirm that every number is a solution. So plugging in numbers is not sufficient because maybe I just got lucky and I picked the 5 solutions, the 5 numbers that were actually solutions, whereas there's another billion that are not. And here we want them to always be true for any number. So how do we do that? Well, there's a few techniques that you can use, and generally what you want to do is you want to take one side of your equation and transform it one step at a time using identities that we already know. Okay, we're transforming it. Transforming it into what? Eventually, we want this to transform into this. Or maybe we could start from this side and transform this one step at a time using identities that we do know are true until eventually it looks like this. Generally, you want to start with the side that is more complicated. You want to take the more complicated side and change it using known identities to make it simpler. Now, which one is more complicated sometimes is obvious, sometimes is not. Sometimes it's a matter of opinion. Some people think one side will be more complicated, some people will think the other. So when we say the more complicated side, what we mean is whichever one has the most number of operations that's being squared, added, and divided. However, sometimes you'll have two that are comparable, two that are pretty much equal in complexity. In that case, just pick whichever one you like. However, here it's pretty obvious. This is a single function. Here you have several functions with several operations. This is definitely the more complicated part. Okay, so to confirm the identity, begin with the more complicated part. And again, that won't always be obvious. And if it's not obvious which one's the more complicated one, well then just pick one. The worst that can happen is you'll pick the one that's not as complicated, and so the problem that you do will be just a little longer. All right. So now what we're going to do is we're going to take this and we're going to use identities that we are sure are true. For now, we don't have very many Pythagorean identities, some in the reciprocal identities and the quotient identities. And we're going to transform this into eventually we get, hopefully, this. Well, right off the bat, I recognize this. Tangent squared of theta plus 1, that's a Pythagorean identity. So here, this is equal to secant squared of theta, like that. Here, I'm going to even label that. What is this? This is the Pythagorean identity. I don't want to have to write the whole thing out, so I'm just going to write Pyth for Pythagorean, just as a little note of what I did. The denominator, well, I don't recognize it as being anything immediately something that can immediately simplify, so for now I'm going to rewrite this. And generally, that's what we want to do. We want to handle these one step at a time. Too many steps at once tends to cause mistakes. Okay, well notice, secant squared of theta, that means secant of theta times secant of theta. And that's not even an identity, a trigonometric identity. That's just what square means, right? Square means something times itself. So here, that's not even a trigonometric identity. That's just some arithmetic. I know what squaring means. It means some multiply something times itself. Oh, but now, notice, secant of theta divides secant of theta, which becomes the number 1. Right? A number divided by itself is 1. And so this becomes just the secant of theta times 1, which is just the secant of theta. And there we go. I'm sure this is equal to this because of the Pythagorean identity. I'm sure this is equal to this because of some arithmetic. I know what squaring means. And I know that this is equal to this because, again, some more arithmetic. Here I'll put division. I've divided those, and I'm left with this. So if this is equal to this, and this is equal to this, and this is equal to this, well then cutting out the ones in the middle tells you, oh, this is equal to that. So this confirms that it's not just sometimes where it's equal, but this is always equal to this, no matter what. And so this verifies our identity. This is one of the first times that you see a problem like this. In this case, you were already told the answer. You were already told, hey, this equals this. Right? If you say this equals this, well, you already kind of knew that. That was part of the question. Here, the answer isn't this final part. The answer is these two steps in the middle. That this, by the Pythagorean identity, is equal to that. This, by squaring, is equal to this. And this, by division, is equal to this. So here, the answer, you've seen me at the end of most problems, I'll put a little box around the answer. Here, I wouldn't put a box around this because this is not the answer. The answer is this entire process. If you say this is equal to that, well, that's true, but that's something we already knew. It's the steps that tell you that these are equal that is the answer to this kind of a question. When you say verify an identity, we want the entire procedure. All right. So let's see some more of those. All right, let's consider an equation that looks like this. We're going to take secant of theta minus tangent of theta, and then that whole thing is being squared. Now we're going to add 1 to that, and we're going to divide the entire expression by secant of theta times cosecant of theta minus tangent of theta times cosecant of theta, and that whole thing is said to be equal to 2 times the tangent of theta. And again, the question is to verify the identity, so really we think that's true, but the question is we need to show that that's true. We need to prove it. Right? This is proving it, that this is equal to this. All right, so once again, you can start from either side. You can either start with this side and try to write it one step at a time until it turns into that, or take that and one step at a time turn it into this. It's sort of a matter of opinion which way we should go. You could start from either side. However, most people, especially when you're first learning to do this, will have an easier time starting with the part that's more complicated. It's simpler to take something big and break it down into smaller pieces than it is to take something small and build it up to something this complicated. So we're going to start from this side. All right, secant of theta minus tangent of theta, quantity squared, plus 1 over secant of theta, cosecant of theta, minus tangent of theta, cosecant of theta. Okay. All right, so what we want to do is we want to use identities that we already know. Looking at these expressions, I don't really see any identities though. I kind of see a Pythagorean identity, but not quite, because if this was tangent squared of theta plus 1, okay, that's different. But here that's cosecant of theta minus tangent of theta squared plus 1. So nothing here immediately stands out as being an identity, at least not yet. We'll notice that in the previous problem, we did use a known identity, namely the Pythagorean identity, but we also just used some algebra, in fact, some arithmetic. That's going to be a very common thing. Sometimes, if you don't have any identities the way things are written, we might want to rewrite them by using not the rules of trigonometry, but just arithmetic. Hey, look, I'm squaring something. I know how to square something. It means multiply it times itself. So here, I'm going to take that and I'm going to square it. I'm not going to worry about the plus 1, just all this other stuff. All right, so secant of theta minus tangent of theta. Let me go ahead and do this off to the side over here. If I take secant of theta minus tangent of theta, and I square it, that's the same as saying secant of theta minus tangent of theta times itself. That's what squaring something means. It means multiply times itself. All right, so secant of theta times secant of theta, that's secant squared of theta. Secant of theta times negative tangent of theta, well, that's negative secant of theta tangent of theta. Then I do it again. Negative tangent of theta times secant of theta, well, that's going to be negative, and well, that's the same thing, right? Secant times tangent, negative secant of theta tangent of theta. And then negative tangent of theta times another negative tangent of theta, double negative makes that a positive, tangent of theta times tangent of theta, that's plus tangent squared of theta. So here I can take this part that I've just squared and write it as secant of theta squared. Here I have minus secant of theta tangent of theta minus another secant theta tangent theta. That gives me minus double secant theta tangent theta. combine my like terms. And then plus tangent squared of theta. And then I have plus 1 right here. And all of that is being divided by secant of theta, cosecant of theta, minus tangent of theta, cosecant of theta. Now, I do recognize a Pythagorean identity. I didn't before, but now I note that tangent squared of theta plus 1 is secant squared of theta. So I'm going to take this part right here and replace it with secant squared of theta. All right, so now I'm left with secant squared of theta minus double secant of theta tangent of theta plus, and then that part there becomes secant squared of theta. So far I haven't changed my denominator. I'm going to leave it the way it is. So it's going to be secant of theta cosecant of theta minus tangent of theta cosecant of theta. So notice what I've done. First of all, I've squared this, so that's just some arithmetic. In fact, let me even just write square. I squared. Then, from here to here was a Pythagorean identity. That tangent squared of theta plus 1 became secant squared of theta. And now notice I have some like terms that I can combine. That secant squared of theta plus another secant squared of theta, well, that's just double secant squared of theta. So 2 secant squared of theta minus 2 secant of theta tangent of theta over secant of theta cosecant of theta minus tangent of theta that should be cosecant of theta. And again, all I've done here is I've combined my like terms. I literally just added. So from here to here, I went ahead and I add. Okay. Now, at this point, I note that I have, in my numerator, I can do something algebraic. Namely, hey look, I have a 2 and a secant in both of these terms. That's a common factor. If I think back to algebra, that means I can factor out 2 secant of theta. Same thing over here. I notice that I have cosecant of theta and cosecant of theta. That's a common factor. So I can factor that out. So here I can write this as 2 secant of theta. That's the common factor. But now, times, well, let's see. If I divide that by secant of 2 secant of theta, I get secant of theta. Minus, if I divide this by 2 secant of theta, I'm left with just tangent of theta. And I can do the same thing in my denominator. Cosecant of theta is common to both. So that's cosecant of theta. If I divide that by cosecant of theta, I'm left with just secant of theta. Minus, and if I divide out the cosecant of theta here, I'm just left with the tangent of theta. This doesn't happen too often, but it is still a possibility. Sometimes we need to factor. You'll note that factoring is the correct thing to do whenever you notice that you have a common factor, something that looks the same in more than one term. Here I see a couple of 2's. So right away that tells me factoring is probably going to be true, something I'm going to use. Once I realize that that's something I need to use, well, let me go through and see if I can find other stuff that's common. Oh, there's a secant that's common. Hey, there's a cosecant that's common. So here I went ahead and factored. This is trigonometry, which means we've learned new trigonometric functions and new trigonometric identities, but we don't let go of algebra. We still know how to square things, add things, and factor. Algebra is still in play. Note now that in this are identical, which means I can divide them. Secant of theta minus tangent of theta divided by itself is just the number 1. So here, just by regular old division, that's going to be, well, these divide away, and I'm left with just 2 secant of theta over cosecant of theta. Just like that. that's looking a lot more like what we had up here. I have 2 times, okay, well that's still a little more complicated. But I have some identities that let me rewrite these in terms of other functions. In particular, I know that the secant is the reciprocal of the cosine function, and the cosecant is the reciprocal of the sine function. So here what I'm going to do is I'm going to separate these out. I know I want to deal with these separately. This is going to change into the reciprocal of something, and so is that one. So here, let me write these as 3 separate things. Let me write this as 2 times secant of theta times 1 over the cosecant of theta. That part isn't necessary. You could work from here, but personally I find it easier to separate my factors into separate pieces and then just work with them separately rather than have to deal with them all at once. All right, so here, that number 2, well, that looks like something that I want to keep there, so let me not even worry about that. Let me work with these 2. I know secant of theta is the reciprocal of the cosine function. So I can write this as, and normally I'd come over here, but let me just write them directly underneath so that we can compare. Let me leave that as a 2. Secant of theta is 1 over the cosine of theta. And notice, 1 over the cosecant of theta, well, that's just the sine of theta. Remember, sine and cosecant are reciprocal functions. So 1 over the cosecant of theta, the reciprocal of the cosecant of theta, is just the sine of theta. And if I multiply these all back together, that's going to be 2 times sine of theta. And then the denominator is cosine of theta. Oh, but now by the quotient identity, sine of theta divided by cosine of theta is tangent of theta. And that brings us to our result. And there we go. Note, this is not the only way to confirm this. Recall that we have seen other identities that cover sine and cosine, tangent, secant, cosecant, and cotangent. So here, this was one way to transform this into this. It's not the only way. This is just the first way that I personally thought of. But if you have a different way to go about it, it might be slightly shorter, or it might be slightly longer, or it might be about the same size, but look different. And that's okay. One of the nicest things about these kinds of problems is also one of the most annoying things about these kinds of problems is that there is no single correct way to do it. In fact, there's not even a single 20 correct ways to do it, right? There's dozens, if not hundreds of ways to do any of these problems. And as long as each step is equivalent, is equal to the step before it, and each step is equal to the step after it, all dozen or 100 different ways are all correct. All right? So the nice thing is you can never really be stuck. As long as you can think of a way to rewrite this in some other way that looks different from where you started, and as long as you keep doing that, eventually you will end up with the correct result. You will end up proving that this is the same as this. The annoying part is because you're never really sure which one is the best way, even though they're all correct, even though if you're not sure which one the best way is, well, sometimes your problems can be a little long. But with experience, we learn how to cut down on that as well. So go ahead and give one of these a try. See if you can verify the following identity. We're going to take 1 over 1 minus the sine of theta plus 1 over 1 plus the sine of theta. These are almost identical. That's a minus, that's a plus. Otherwise, they're the same. That's equal to double the secant squared of theta. Okay? Verify that identity. Transform one side one step at a time until you can get the other side. It doesn't technically matter which one you start with. However, you will usually find it simpler to pick the side that has the most number of operations and the most trig functions, the one with the most stuff going on, and start from that side. So go ahead and pause the video and give this a try. And when you get an answer, go ahead and unpause the video and we can go through it together. All right, so let's take a look. Okay, personally, I would prefer starting on this side. It looks more complicated, and generally it's going to be easier to take something complicated and simplify it than to take something simple and build it up. So I'm going to start from this side. I don't see any identities at all. There's nothing here that I could rewrite in any meaningful way. But once again, aside from just identities like the Pythagorean identity, and I never labeled this one up here, did I? This was the reciprocal identities. And this was the quotient identity. Aside from the known trigonometric identities, the Pythagorean, the reciprocal, and the quotient identities, we've also been using just regular algebra, regular operations. And in fact, that's what we want to do here. I notice I have addition. So let me add. Let me start off with 1 over 1 minus the sine of theta plus 1 over 1 plus the sine of theta, minus and plus. And in order to add those, notice those are fractions. So I need a common denominator. Let me multiply this side by 1 plus the sine of theta. And let me multiply this by 1 plus the, I guess it should be 1 minus the sine of theta. Because notice now they have the exact same denominator. That times that. But of course, since this is a fraction, whenever I change the bottom, I need to change the top. Otherwise, I've rewritten my fraction in a different way. So here I need the top and bottom to still be scaled the same way. And likewise, if I multiply this by 1 minus sine of theta, I need to multiply this by 1 minus the sine of theta. Okay? Whatever you do at the bottom, you do on top. So now let's see what we have. All right. That's 1 plus the sine of theta plus 1 minus the sine of theta. And since these have a common denominator, let me write them all together as a common denominator, all together. Here, the common denominator is this times this. Right? 1 minus sine of theta times 1 plus the sine of theta. All right, so let's go ahead and do that. If we multiply those together, 1 times 1 is 1. Okay, good. 1 times sine of theta is sine of theta, and that's positive. Negative sine of theta times 1, that's minus sine of theta. And then negative sine of theta times positive sine of theta is negative sine squared of theta. Notice these two can combine. So from here to here, all I did was I went ahead and added. Found a common denominator and added. And then when I actually do the adding, notice that these two divide out, subtract out rather. And in fact, so do these. Hey, look, sine of theta minus sine of theta, that's gone. So here, we're left with 1 plus 1, well, that's just 2, over 1, these are both gone, 1 minus sine squared of theta. Okay, 1 minus sine squared of theta. To go from here to here, all I did was I simplified. I combined my like terms is what I did. All right, well now 1 minus sine squared of theta, by the Pythagorean identity, that's the cosine squared of theta. After all, going back to our previous section, the Pythagorean identity states that cosine squared of theta plus sine squared of theta is equal to 1. So if I subtract sine squared of theta from both sides, 1 minus sine squared of theta is now over here, and this is gone now. So 1 minus sine squared of theta equals cosine squared of theta. 1 minus sine squared of theta, well, that's equal to cosine squared of theta. That's the Pythagorean identity. All right, well, here. Let me write this as 2 times 1 over cosine squared of theta. Again, that's a personal habit. Whenever I'm going to change some parts and not others, I like to write them separately, just like I did up here. If you went ahead and worked with it the way it was there, that's fine too. That is also correct. So now, 1 over cosine squared of theta. Well, that's the reciprocal identity. After all, 1 over the cosine of theta is the secant of theta. Oh, but that's being squared. Okay, so it's going to be secant squared of theta. So this will give us 2 times the secant squared of theta. And again, that's the reciprocal identity. But that's the conclusion that we were hoping for. So by first adding these together and then simplifying, combining like terms, using a Pythagorean identity, and then using the reciprocal function, the reciprocal identity, we end up with the function that we were looking for. And so this verifies our identity. Once again, this is not your answer. You already knew that was going to happen, or at least you were hoping that was going to happen. That's what you were trying for. The answer is not this step. The answer is all of these steps. So this entire process is your answer. Let's take a look at another one. Let's say, for example, we want to verify the identity one minus the cosine of the angle theta over 1 plus the cosine of the angle theta is equal to 2 times the cosecant squared of theta minus 2 times the cosecant of theta times the cotangent of theta minus 1. All right, so let's give this a try. This is one where, which one is more complicated? Which one should we start with? This one's kind of a matter of opinion. I mean, here I have, what let's see, I have a square, multiplication, a couple of subtractions. Here I have addition, a subtraction, a couple of constants, and a quotient. Yeah, it's really hard to tell which one to start with. So this is one of those times where it's sort of a matter of opinion. Which one do you think is more complicated? That may depend. Half of you may think one side, half of you may think the other side. Personally, I'm going to start from this side. And the reason I'm going to start from this side is because here I have 2 different trig functions, whereas here I only have 1. And to me, that makes that more complicated. But again, that's a matter of opinion. So I'm going to start from this side. 2 cosecant squared of theta minus 2 cosecant of theta times cotangent of theta minus 1. Now, in this case, I note that I don't really have a nice place to start. The reciprocal identities, the quotient identities, the Pythagorean identities, none of them immediately jump out at me. Here that almost looks like a Pythagorean identity, but not quite. So sometimes the reason that it looks unfamiliar or complicated is because you have too many trig functions around. One thing that is useful is at the very beginning, if no identity immediately jumps out at you, if you don't immediately see, oh yeah, this is the quotient identity, or oh yeah, this is the Pythagorean identity, or later on the sum and difference identity, or any other one. And if you don't immediately see any arithmetic that you can try, oh look, I can add those, or I can divide those. If none of that works, one thing you might try is rewriting everything in terms of another trig function. After all, every trig function can be rewritten in terms of another one, and in particular, sine and cosine is easy to use compared to any other. So here I'm going to write this the following way. I know the cosecant of theta is the same as 1 over the sine of theta. Okay, so cosecant squared of theta, well, I'm going to leave my 2 there. Cosecant of theta is 1 over the sine of theta. So the cosecant squared of theta is 1 over the sine squared of theta. Minus, I'm going to leave that 2 alone. Cosecant of theta is 1 over the sine of theta. Cotangent of theta is cosine of theta over sine of theta. And again, that's the quotient identity for the cotangent. Here I'm using the reciprocal identity for cosecant. And then that's just a constant, so I'll leave it as minus 1. Here, let me rewrite these. Notice that I have a common denominator here. Sine squared of theta. And over here I also have sine squared of theta. Oh, but this one doesn't. Well, we can give it 1. If we divide the top, and if we multiply the top and bottom by sine squared of theta, hey look, now all 3 of them have the same denominator. So let me put all that together. Let me write that as, well, my common denominator is just going to be sine squared of theta. And my numerator is, well, let's see, that's the number 2, minus 2 cosine of theta, minus sine squared of theta. Just like that. Common denominator, sine squared of theta, 2 minus 2 cosine of theta minus sine squared of theta. Now at this point, anyone who wants to divide sine squared of theta and sine squared of theta, you should be ashamed of yourself. Remember, you can only divide if you have this as a factor, not if it's as a term. The reason I bring that up is because every semester I have, maybe 1/4 of the class wants to do that. Don't do that. Here, what we want to do is we want to note, okay, what am I trying to get? Well, I'm trying to get this. I'm trying to get 1 minus cosine of theta over 1 plus the cosine of theta. Oh yeah, that means I should only have cosines. There shouldn't be any sine of anything here. Okay, so these sines squared of theta are something I want to get rid of. Well, yeah, but you just said you can't divide them. Well, that's true, but that's not the only way to get rid of something. I can use a Pythagorean identity. I can say the following. 2 minus 2 cosine of theta minus, and now this sine squared of theta that stays the same, that stays the same, minus, but now this, by the Pythagorean identity, is 1 minus cosine squared of theta. Same thing over here. Sine squared of theta can be written as 1 minus cosine squared of theta. This is equal to this. If you don't believe that, add cosine squared to both sides. Oh, well, that would make that go away. And I would have sine squared of theta plus cosine squared of theta, which we know is equal to 1. So yeah, that's true. Sine squared of theta is equal to 1 minus cosine squared of theta. All right, so now I have some stuff I can simplify. Notice I can combine some terms here. So here I can write this as, let's see, 2 minus 1, that's just the number 1, minus 2 cosine of theta, minus a minus, oh, that's going to become a plus, cosine squared of theta. Over 1 minus the cosine squared of theta. Just like that. And now, we're going to pull off a trick that we first learned in algebra. We're going to factor these expressions. So let's go ahead and do this off to the side a bit. Here, we're going to be using a technique from algebra called factoring by substitution. And let me just go ahead and do that. Let's go ahead and do this down here. So let's factor this one right here. 1 minus 2 cosine of theta plus cosine squared of theta. I'll factor that numerator. All right, factoring by substitution works this way. Okay, I have multiple copies of cosine of theta. Let me call those x. So let x equal to the cosine of the angle theta. So this can be rewritten as 1 minus 2x, that cosine of theta becomes that x, plus x squared. Cosine squared is x squared. All right, and now we factor this. Okay, well then that's going to be the same as 1 x squared minus 2x plus 1. All I've done is I've rewritten the order. Gone ahead and written in descending order. And now that factors out nicely. I can write this as x minus 1 times x minus 1. All right. Two numbers that multiply to give me 1 add up to give me negative 2. But now, since x is equal to the cosine of theta, I can now bring this back and write this as cosine of theta minus 1 times cosine of theta plus 1. Just like that. So this is the factorization of my expression here. So I can now rewrite that numerator as cosine of theta minus 1 times cosine of theta plus 1. And, oh, sorry, that should actually be, that's minus 1, that's minus 1, that's minus 1. That should also be minus 1. I changed that to a plus for no good reason. That should be a minus just like that. Okay, and we can do the same thing for this denominator. We can say, okay, let's factor 1 minus the cosine squared of theta. Again, I can use the same substitution. I can write this as 1 minus x squared. Oh, that's the difference of squares. We see that all the time in algebra. The difference of squares factors as 1 minus x times 1 plus x, which we can write as, well, x is equal to the cosine of theta. We can write this as 1 minus the cosine of theta times 1 plus the cosine of theta. So that's our denominator. 1 minus the cosine of theta times 1 plus the cosine of theta. Just like that. We do know that here these divide out, well, almost. They're in the opposite order, but that's okay, because we can write this way. We can say this is negative 1 minus cosine of theta. If you distribute, that becomes a negative 1, just like this one. And negative of a negative, that makes it a positive 1, just like this one. Okay? So, now that these are exactly the same, I can divide them out. All right? So these divide away. And my denominator is 1 plus the cosine of the angle theta. Here in my numerator, there's a negative on the outside. Let me go ahead and distribute that negative. Negative of a negative makes that a positive 1, and the negative cosine of theta. And that is exactly what we were after. So this one is a bit more complicated than any of the other ones we've seen, which is why I wanted to see that, show this example so that you could see the different techniques as they work, and also see that every once in a while you're going to have some that are a little longer. Some of these problems are going to be a bit longer than you might be used to. They're not 1 or 2 step problems, but that doesn't mean you're doing anything wrong. In some cases, you'll do a problem and it'll take you 1, 2, 3, 4, 5, 6, 7, 8 steps and a little side work. And that doesn't mean you're doing anything wrong, and it doesn't mean there's anything wrong with the technique that you have. It just means some problems are long. And that's it in terms of examples. What I do have is a little bit of a summary here. Note that in this section we don't really have any formulas or any concrete techniques, but we do have some guidelines. For every problem here, what we have is we have an identity. We have an equation where we're trying to confirm that the left side and the right side are identical for all values of theta. And in order to do that, we have a few guidelines. There is no one way to do it. In fact, that's one of the guidelines. We want to start working on the more complicated side. Now, sometimes that's a matter of opinion, but generally speaking, it's the one that has the most number of operations and the most number of trig functions. It is possible to start from either side, but you'll find it simpler to start from the more complicated side. What you want to do is you want to use the simple trig identities that we know to try to confirm the bigger trig identities that we want. Use the basic trig identities and algebra, meaning using factoring and the operations, addition, subtraction, multiplication, and division. Using trig identities and algebra, you're going to rewrite the expression little by little. Note, at no time did I make any major leap. I've transformed one piece at a time. If no identity or algebra is apparent, meaning, okay, I did my best and I still can't find any of these that work, writing everything in terms of cosine and sine. That tends to simplify things just enough that some algebra or some identity that wasn't apparent before now seems a little clearer. Oh yeah, that's one I probably want to use. Note there are many correct ways. Each of these problems I've shown you one way to do them. It's not the only way, and it may not even be the best way. Frankly, I picked problems out of a textbook and decided, okay, I'm just going to go through and show a way to do it. I didn't confirm that this is the shortest way. I hope it's not terribly long, but it may not be the best way. But that's okay, because there are many correct ways. And finally, the last guideline is sometimes these problems can feel a little discouraging because they seem to keep going. It seems like, oh, I don't have any direction. I'm not sure what I'm supposed to do. Keep trying. Because although some methods are faster than others, some are a little bit shorter, some have more steps, some have less, as long as at each step you have changed your expression in a way that's still valid, then it doesn't matter if you use one step or two or three or four or five. As long as each step is equivalent to the one before it and to the one after it, it's still correct. So keep trying, because even if you feel like, oh, this is taking too long, as long as you keep moving forward, you will eventually get the result that you like or the result that you need. So that is it for this section. If anybody has any questions, comments, or problems, please make a note of those and let me know during our office hours, during our next session, during our next meeting. I hope everyone has a nice day.